The ILM removal in the treatment of the macular hole has become slowly but surely almost irreplaceable, even if we have many ways to better visualize it. Yet, there are many differences within the gas injection procedure because of a lack of knowledge in the gas expansion and/or absorption properties. The goal of this film is to make us think about that. We want to exert, without any risk of hypertonia, an important pressure on the macular hole for a certain period. We don't know exactly how long for. It probably depends on the clinical stage of the macular hole, on individual cellular reaction, and on the positioning observance. 5 to 6 days are more than enough in any case. A couple of days are not sufficient in stage 3 or 4. In order to keep a safety margin, let's say we need to exert a good pressure during the 3 to 5 first days. What does a good pressure mean? The force exerted on the macular hole is a flotation force equal to the pressure of a water column as high as the bubble. In an hemetropic phakic eye, the exerted pressure will be proportional to the eighth of the bubble as long as the bubble reaches the passer capsule at 14.5 mm from the macular hole. Now, if we consider the pressure according not to the eighth but to the volume of the bubble, we can verify that the pressure increases up to a volume of 3.5 cc. It will not be higher for a bigger volume. However, filling completely the vitreous cavity will expose the eye to hypertonia risk at the slightest gas expansion. In conclusion, a good pressure, let's say more than 80% of maximum pressure, will be obtained by a bubble of at least 2.7 cc. At that moment, the exerted pressure will be slightly over 0.8 mm of mercury, just like a coin underwater could exert on the underlying tissue. We can also understand the patient positioning effects. If he looks 30 degrees higher, the eighth of the bubble underneath the macular hole, and therefore the pressure here exerted, will have considerably decreased. Once injected in the eye, gases has different expansion and absorption properties. The hair does not expand. A fast diffusion into the bloodstream results in a medium half-life of 1.3 days. It disappears after 5 to 6 days. Injected alone, it will not induce a sufficiently long and powerful tamponade. The expansible gases have an absorption capacity similar to the hair, but there is a diffusion of nitrogen and in a lower part carbon dioxide and oxygen from the bloodstream into the bubble, resulting in a final expansion. Let's see what happened for the two most popular gases. A bubble of C3F8 has a predicted expansion of 4 within at least 3 days and a half-life of 7.5 days after expansion. It disappears within 55 to 65 days. It will thus not be convenient for this requested short tamponade. A bubble of SF6 has a predicted expansion of 2 to 2.1 within 1 day and a half-life of 2.5 days after expansion. It disappears within 10 to 14 days. It seems thus to be much more adapted to this kind of surgery. (1.8 cc of pure SF6 can be injected in a 4 cc vitreous cavity without any risk, as the bubble will expand by 2 to 2.1. However, the immediate pressure exerted during the first day will not be sufficient. In order to have an immediate higher pressure, A complete filling of the vitreous cavity with a mixture of SF6 plus air has been invented and has become the standard technique. The problem is that the sole available space the SF6 will find to expand is the space left thanks to air absorption during the first day. The mixture must absolutely not be expansible. This is why we generally use a 20% SF6 mixture. How will this mixture react in an emmetropic phakic eye? 4 cc of 20% SF6 means 3.2 cc of air and 0.8 cc of SF6. 50% of the air will be absorbed every 1.3 days, the half-life for air. After 1 day, the 0.8 cc of SF6 will have doubled. 2.5 days later, we will have 0.8 cc's, and within 6 more days, 0.4. At least 80% of the maximum pressure will be exerted during 1.5 days. I think this technique is a little bit discouraging. In fact, we spend a huge amount of time and efforts to achieve a complete gas exchange, and the only result is 1.5 days of satisfying force. This is why I propose the following technique. 3 cc's of 50% SF6 mixture are injected in a phakic eye, 3.3 in a pseudophakic. This will induce an immediate pressure very close to the possible maximum, but it will give 1 free cc of BSS available for SF6 expansion. 1.5 cc's SF6, which is twice the quantity used in the standard technique, can be injected. The air will be absorbed as seen before. After 1 day, the SF6 will double and reach 3 cc's, so the maximum volume will be 3.8 cc's. 2.5 days later, 1.5 cc's of SF6 will still persist. A good pressure of at least 80% of the maximum rate will be exerted during 3 days, which is about the double compared to the standard technique. But the other advantage of this technique is its simplicity. After closing hermetically the sclerotomies, you only have to fill up a syringe with pure SF6, mix 2 cc of it with 2 cc of air, and put a 30 gauge needle at the tip. A 25 gauge needle is entered entirely towards the macula. When some liquid is coming out, the injection begins and will be stopped when bubbles of gas appear in the 25 gauge needle. This is to say, in practice, when 3 cc in a phakic eye and 3.3 in a pseudophakic have been injected. The 2 needles are then removed in the same time. The entire procedure has taken less than 1 minute to be achieved. Some tips increase the exact reproduction of this technique. Avoid vicryl suture. Prefer a monofilament, which elasticity provides a stronger closing and decreases the leakage risk during injection. The exact control of the technique depends on the gas concentration level, which can vary according to the quantity left in the bottle. Disposable bottles avoid such problems and have become for me irreplaceable. No risk to damage the retina, since the 25 gauge needle length is 16 mm long, so 3 to 4 mm will separate the needle from the macula. Wait for the BSS to appear in the 25 gauge needle before injection. If the needle happen to be non-permeable or blocked by some vitreous, you might undergo a hypertonia risk. As you see, as for